There is only one perfect solution, but there are clues that will try to trick our team.
Hello there everyone, my name is Crazy Caleb, and welcome to Abstract Sequences. This is a module that I put off for a long time due to it being sort of a rare module to see on any bombs, for that matter of fact, and I'm going to explain to you how this module works. So let's get into it. So the first things first that I immediately want to do is I want to note down this 4x4 grid of numbers here, and of course if there happens to be one-digit numbers, I'm going to put a 0 before them just to help me, just for placement's sake. So, whenever the lights turn back on, that will be nice. But essentially what we're going to do is we're going to be pressing a series of variables here that we're going to figure out, which are going to be permitted after we do a whole bunch of work. So let's get into that. So we have 25, 67, 96, 43, 34, 89, 81, 41, 78, 83, 56, and 09, and 05, 85 to 02, and 75. And now let's note down the 94 on the display there. So now, first things first that we need to do is we need to figure out a set of 3 different variables representing x, y, and z. And this is going to be how we're going to do this. So we're going to use the following table to determine what correct values for the variables are, and we're going to take the reading from the 3 applicable columns and calculate the mean of the data set. So let's do that. So, for x, y, and z, we're going to have to do these 3 columns here, and we're going to have to essentially add up each value and calculate the mean. Now, there's only going to be three applicable columns for each one, and as you can see here, all of these numbers that are present in each of these positions, each of these cells here, are divisible by 3 because of the fact that we're going to be calculating the mean. So it's going to be whatever answer you get, you will be guaranteed to get a good an integer number. No decimals will be present at all. So, if the display is prime or composite, 94 is currently a composite number because it's at least divisible by 2. Any even numbers that are not 2 are composite. So that's any numbers that end with an even number that are not 2 are going to be composite. So that's good to go. If the absolute value of the sum of the first column is even or odd, let's find out. So we have 25 plus 34 plus 78 plus 5 is going to be even or odd. It ends in a 2, so that's going to be even. And finally, is the last digit of the serial number in the range of 0 through 4 inclusively, or 5 through 9? It is a 9, so it's going to be a 5 through 9. And now what we're going to do is we're going to calculate for each individual variable. So for x, we're going to add up 21 plus 30 plus 12, and we're going to divide it by 3 because we're doing the mean. And for the mean, essentially what you're going to do is you're going to take the amount of numbers that you added and divide by that number. So for example, we have 21 plus 30 plus 12, I believe it was. Yep. And we're going to take this sum that we get, and since we are currently adding up 3 individual numbers, we're going to divide 63 by 3, and we're going to get a value of 21, and x is going to be worth 21. Now for Yankee and Zulu, respectively, we're going to do the exact same thing. So Yankee is going to be 48 plus 51 plus 18, 48 plus 51 plus 18, 117 divided by 3 is a 39. That's going to be Yankee. And finally for Zulu, Zulu is going to be 15, 36, and 0, which is going to be, it's still going to be taking the mean of 3, because we're currently adding 3 numbers together. So 15 plus 36, essentially, we're not going to add anything to 0, but we're still going to divide 51 by 3, because there are going to be 3 different numbers divided by 3, which is going to give us a 17. Note that if we were to divide by 2, it would give us a decimal number at the end, which is what we don't want. So we want that, and we're good to go. So now, there will be a series of variable adjustments of which we can make to each individual variable, and these columns, instead of just being only 3 applicable columns, all of these columns could potentially be applicable here. And we're essentially going to do some sort of adjustments to the each of the variables, depending on the visible port types and the visible indicators present on the bomb. So currently we have a parallel and a serial, which is corresponding to here and here, because these are both OR values. If one of these ports is present, then that column applies. And note that all of these columns can potentially apply. Now, visible indicators, it doesn't matter of their lit or unlit status. FRK, we don't have that present here, but we do have an SND, so that's going to be right there. So, with x, we're going to be subtracting 2, subtracting 6, and adding 1, so it's going to be 21 minus 2 minus 6 plus 1 is going to give us a 14. And that's going to be what we'll replace this with, 14. Next up for Yankee, plus 3 minus 1 minus 3. What we can essentially do is we can cancel out that plus 3 and minus 3, and all we need to do is simply subtract 1, which will give us a 38. And finally for Zulu, Zulu is going to be a plus 5 minus 3 minus 4 to 17. So it's going to be 17 plus 5 minus 3 minus 4 is going to be a 15. And just like that, we are good to go. Now for part 2. So this is kind of where things get a little bit interesting. And it's also important to note that we're going to be creating a sequence of numbers. And the first term is going to be an A1. So the smallest number is going to be the first term of the sequence representing A1. So the smallest number that we have from X, Y, and Z here is going to be 14. And 14 is going to be our first term of the sequence. So I'm going to put a comma between that, and let's get this thing going. So for the first half, we need to determine what the display number range is between the display value rather, and the number of battery holders we currently have present on the bomb, because we're going to be establishing the used formula, and it's going to be a first half and a second half. So let's do that. So for the displayed value, we currently have a 94, which is going to be in between the range of 80 through 99. And the number of battery holders we have is currently 1, so this is going to be y squared. Y squared is going to be the first portion of this. And for the second half, it's going to be the number of strikes on the row side, which we currently have 0. We currently don't have anything, as you can see up in the top right. It's going to be that 0, 0 out of 15. That represents our strikes. And the number of ports plus port plates, we currently have 2 ports, we have 2 ports, and we have 2 port plates. That's going to be a 4. So this actually looks like a really simple formula. So all we need to do is we're going to be doing a y squared and an nx n times 5 rather. N times 5. Now, we need to figure out a way how to combine each of these halves together, which we're going to do right down here. What connects these two halves is up to the table below. It is more than one or no applicable columns or rows. If more than one or no applicable columns or rows, use the respective otherwise. So, do we have greater than 3 battery holders? We do not. Do we have 2 plus on the indicators? We do not. The displayed number is odd. It is not, so we're going to be using the otherwise row here. Do we have more than one port type? We do. Do we have the sum of the serial numbers greater than 14? We have a 4 plus 9, which is going to be 13, so that's not greater than 14. Do we have more than 10 modules on the bomb? Nope. And otherwise, which in this case we actually had one apply. We didn't have more than one case before the otherwise apply, and we're simply just going to be using this as a column. So we're going to be combining these guys together with a multiplication sign, or as I like to put it, an asterisk sign. That. So let's take a look, and let's actually pop this in our text field calculator. So we have for our first half, we're going to be doing y squared, which is a 38, quite a large number, 38 squared, and we're going to be multiplying this by n, which is going to be whatever our number is for that stage, because this is where the part gets really, really interesting. We're going to have to calculate a series of integers in a sequence that is going to be up to n equals 20. So we're going to have to essentially plug in skipping 1 because we already have our first term of the sequence, a1. We already have that figured out. So we're just going to start with a 2, and the times this by 5. And in cases like these where the number is actually rather quite large, all we're essentially going to do is we're going to take the number's 2 least significant digits to create a list of all the results or terms. So in this case, our 2 least significant digits is going to be 40, and this is going to be our second part of the digit, a second term in the sequence. Now let's add it. Let's do a 3, which is going to be 60. Then let's do a 4. Let's do an 80. Yep. And I'm starting to have a hunch that this is going to be just simply adding 20 to each individual stage. So that's going to be a 6, which should be 20. Yep. And then it should take me back to 40. And at this point, we're currently looping right now. We are currently looping, and these are essentially the values that we're going to get for our sequence, but just essentially over and over and over. Now, there are many cases where calculating this can be really, really simple. If you happen to get like a plus, for example, that would combine these two guys together, it really, really becomes easy. However, not so much this time around. But what are we going to do? What are we going to do with this? And if any term is less than 0 multiplied by -1, just keep that. So let's take a look. So what we need to do is we need to essentially calculate the terms, and we're going to press all the numbers that do not appear in the sequence. And once you press a button, all the labels on the buttons will disappear. This is why you note this down, because of the fact that all of the buttons will disappear once you begin to press the buttons. So what we need to do is we need to figure out if we have any of these values present on the module, including 14, 40, 60, 80, and 0, and 20 as well. And we're simply going to avoid those values. However, one last thing that we need to check is sort of a unicorn case. If exactly 3 out of the 4 conditions are true, forget all the rules up to this point, and your sequence is the first 20 terms of the Fibonacci sequence, starting with the first one, and still using the 2 least significant digits. If the amount of batteries, when added to the amount of battery holders, is a prime number, 1 plus 1 is equal to 2. That is a prime number, yes. The digital root of the displayed number is a prime number. 9 plus 4, and for those of you who don't know what digital root is essentially, how do you describe this? You have 9, you essentially take all of the digits in this number here, and we're simply going to add them all together until they're 1 digit. So 9 plus 4 will give us a 13, and then 1 plus 3 is going to be a 4. 4 is the digital root of this number. It is not a prime number, so this could be our potentially false rule, and the other rules can be true. The amount of solved modules is a prime number. It is not. 0 is not a prime number, so that is not true. And already, taking a look at this, this is not true. The sum of the 4 corners is a prime number. Just to check for good old time's sake, it would be 25 plus 43 plus 5 plus 75. And that's going to be a no. That's going to be an absolute no. So that's going to be 148. That is not prime number. So this would be the only rule that's true. 3 out of the 4 rules need to be true, so this is not the case. This is a very rare rule to apply, so that's, it's sort of like a unicorn, but again, it can happen. It can happen. So, let's get into the actual module here. So, do we have 14 present on the module, on the actual displays here? From the looks of it, no, we do not. We only have 41. Do we have 20, 40, 60, 80, or 0, 0? 20, 40, 80, 60, 0, 0. No, it does not appear that we have any of those. So what this means is that we're going to be essentially pressing all of these values. Now, there's one last thing that we need to do. You cannot unselect the button once it has been selected, so remember where the labels are and be careful what you press. So we're going to be pressing all the labels, but we need to figure out which order we're going to be pressing them in. If the amount of minutes on the bomb timer is even, press these numbers in ascending order, otherwise descending order. What I tend to do is I actually tend to do ascending order all the time. And one important thing to note is that when you happen to choose whether it be ascending or descending, it's only going to care about it when you submit the actual check mark. It doesn't care about when you press the first button. It only cares about when you press the submit button or this check mark down here at the bottom right. That's what we're going to be doing. So I'm going to wait around for the minutes to be even. I'm going to do it ascending, but I'm going to take my time with it, and let's take a look here. So let's actually start ordering everything up. So we have 2, we have 5, we have 9, and then next up, it looks like it'll be 25, then 34 perhaps, 34, then 41, then 43. There's lots of 80s, that's going to be helpful. And then we have 67. And then we have, or excuse me, 56 before that, 67. Then it's going to be 75, 78. Then we have, after this point, it's going to be 81, 83, 85. Zoom out a little bit here. 89. 90, and then 96, okay? And let's count to make sure that we have all 16 values. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and we're good to go. Alright, so now let's start pressing each of these values into the module in ascending order. So we're going to do a 2. Now, once I press this 2, it will immediately go away. All of these displays will go away, like so. It will all turn into question marks. So then we had 5 at alpha 4. We had 9 at delta 3. We had 25 at alpha 1. And you can see how this is going to work. So 34, then 41, then 43, then 56, then 67, then 75. Right down there. Yep, 75. Then 78. then 81, 83, 85, 89, and 96. Note that I started pressing this on an odd number of minutes, but now it's currently even. We hit that check mark, and all of the buttons will currently start to fall out, and they will be in the order that I press them in. And just like that is a solved module. Now, let's go over one more example, and hopefully I can get a better example of what I mean by you simply need to avoid the calculated values that you get. And we actually had a really easy case because of the fact that we only had 5 guaranteed numbers. But just as a case, just as a reminder, the n equals the first term in the sequence is always just going to be by itself, even if it's unrelated to the actual pattern of the sequence. So in this case, if it was 1, it would be 20. We simply ignore that. We simply are going to ignore that, and we're simply going to immediately go to step 2. That's the way that this works. So let's do one more example. This module it's not played with often, and it has its reasons why. It takes a little bit longer to do, and especially with calculating that all 20 sequence can take a while, so that's going to be a bit annoying.
There is only one.
So let's go over one more example.
Clues that will try to trick our team.
All right, and we have on the module, we have 87, 27, 60, 07, 92, 99, 68, 17, 29, 20, 93, and 81, and 01, 02, 21, and 45. So let's go up here and let's calculate our x, y, and z. X, y, and z. And we have a display value of 48. Okay. Let's scroll this down enough so that I have just enough to see my edge right at the top here. So if the display number is 48 is currently a composite number, it's not prime, it's even again. You're going to have a lot of composite cases because prime is definitely a lot rarer than the prime. If the absolute value of the sum of the first column is even or odd, so let's do that. So we have 87, 87 plus 92 plus 29 plus 1 is going to be 209. That is going to be odd in this number. And finally, if the last digit of the serial number is between 0 through 4 or 5 through 9, it is a 0, so that's going to be 0 through 4. So let's calculate the mean of each of these variables. So we have 21 plus 33 plus 42. 21 plus 33 plus 42 is going to be 96. 96, let's divide you by 3, is going to be a 32. Yankee, 48, 9, and 24. 48, 9, and 24 is going to be 81. 81 divided by 3 is going to be 27. And finally, Zulu is going to be 15, 45, and 6. 15, 45, and 6 is going to be 66, which should be 22 if I can do my math correctly. It is indeed 22. Now let's do a little bit of adjustment. Let's do a couple adjustments. We have a parallel and serial again for the visible four types, and we have an FRK. FRK does not correspond to any of these indicators, so that's going to be good to go. We're going to ignore those, and we're going to subtract 8 from x. So 32 minus 8 is going to be a 24. Yankee is going to be a plus 3 minus 1, so plus 2 is going to be 29. And Zulu is going to be plus 5 minus 3, that's going to be a plus 2, is going to be 24. And now we're going to take the smallest value, and in this case we have a tie of 24. This is still the smallest number, we're going to take the 24. And that is going to be our first term of the sequence. So, let's get into the establishing the formula. So for the first half, the displayed value is between 40 and 59. So that's going to be 48 right there, in between that little range. Now the number of battery holders by itself is going to be 0. We don't have any batteries on this bomb, so it's going to be Zulu times n minus 1. So let's take a look here. Now for the second half, we still have 0 strikes. Just try not to get them. And the number of ports plus port plates is also a 4 again. So it's going to be n times 5. So we actually have 2 cases where n applies. So we're going to be applying n in 2 parts. This will be very interesting to see. So now how are we going to combine these guys together? So let's find out. More than one port type, that is true. The sum of the serial number digits is greater than 14, not true. And there is not more than 10 modules on the bomb, so it's going to be true. This is the column that applies. Greater than 3 battery holders present, nope. 2 plus on the indicators, nope. And the display number is odd, nope. It's going to be a multiply again. Alright. So let's combine these two guys together. So we have Zulu. Zulu corresponds to 24. 24 times n minus 1 times n times 5. Quite a bit we have to work with here. So let's plug in 2 is going to be 40. 3 is going to be 20. Oh, don't tell me we got the same sort of pattern again. 4 is going to be 40. Oh, you gotta be kidding me. Is this going back and forth? Okay. 5 is going to be right there. We're getting the same pattern again. 6 and 6 is going to be 0, 0. This is an interesting case. 7 and 7 is going to be 40. 8 and 8 is going to be 20. Having a hunch that it's not really going anywhere. 40, again. So what are we going to do? Go back down to 2 zeros? Yeah, this is the same pattern, like the repeating pattern. Back to 2 zeros, yep. So this is going to be our pattern. We have 40, 20, 40, 0, 0, 40, 20, 40, 0, 0. We have the exact same pattern, so this means that this is going to be all of our values. This sometimes is the case, which you can get through easily, but let's take a look and see if there's anything on the module that we can't click. So that we have the 24. 24 is not present. We have the 40. 40 is not present. 20, however, is present. So we're simply actually going to be ignoring the 20 here, and we're simply never going to press you. So I'm already going to mark this out with 2 X's because we're never going to press you ever. Because of the fact that it was in our sequence, in there some way, shape, or form, it's going to be ignored, and we're never going to press that. That's the way that this works. So let's make sure that we don't have any Fibonacci sequence cases that apply. The amount of sub-modules is a prime number. The amount of batteries when added to the battery holders is a prime number. Already, that's going to be a no. We have 0 batteries and 0 battery holders. 0 is not a prime number. And the amount of sub-modules being 0 as well is not a prime number. So this is already going to be false. Moving on to the next one. So let's do sort of the same ascending order. I tend to do ascending order really, really well. I like that a lot. And we're going to be pressing everything except the 20. So we're going to do 1, 2. That looks like it's going to be 7, then 17, then 21, then 27, then 29, and then it jumps up a little bit. This goes to 45, and then it jumps up a little bit more. It goes to 60, then 68, then 81, then 87, then 92, then 99. That should be 15, I think. Oh, excuse me, 93. 93, then 99. Alright, let's count that. We have everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, we have all 15 values here, and that's going to be good to go. So let's start inputting this into the module. Let's do a 1, then a 2, then a 7, then a 17, then 21, then 27, then 29, then 45, then 60, then 68, then 81, then 87, then 92, 93, and 99. We're submitting on an even minute, which is going to be the ascending order, which we need to do, and that should be good to go. Looking good so far. And just like that, my friends, is a solid module. So we had that 20 that was present in the actual sequence, and we simply did not want to press that at all. So that means that we had a solid module. So just one thing to keep in mind is that it is when you press the submit button, that is when it cares about the even or odd minutes. That's when it's going to do that. So keep that in mind, that it is only the submit button, not when you start pressing the sequence of buttons. So as always, thank you guys for watching. Remember to stay crazy, stay cool, and I'll see you guys in the next one. Bye-bye.